Hi everyone. Today we're going to be talking about MiniMax with the alpha beta pruning optimization. Later in the video, we're going to be implementing the various algorithms using the Mancala game as a demonstration. But before we jump into all of the Python code and everything, I want to first review what MiniMax is, and then later what alpha beta is, to get a good conceptual framework before we start touching code. Now, if you're already familiar with the conceptual framework and you just want to see how the code might look, feel free to jump to the later parts of the video. We have a table of contents in the show notes. Otherwise, we're going to start talking about the MiniMax algorithm. So the big kind of question is, what is MiniMax? So at its most general level, MiniMax is just an optimization algorithm based on graph traversal. Now, you might be asking, what are we optimizing? So any game is simply a graph where you've got your current game state here, and you've got all your future positions, and they're all kind of interconnected by the various moves that you can make. And what you're trying to optimize is, at this current game state, what direction, so which one of these three directions should we go? And that sort of depends on all of the game states down below in this kind of future position part of the graph. And it really kind of makes intuitive sense, I think, at least, and I'm sure many of you do this when you're playing games. When you're about to make your move, you think about what your opponent's going to do, and then how you're going to respond to your opponent, and then how your opponent's going to respond to you, or your response, and then so on and so forth, as far as you can think without tiring yourself out. Well, the good thing about AIs, at least, or I guess computer programs in general, is that they don't get as tired as we do. So they can look, many, many moves ahead. So while we might be able to look 2 moves ahead, which is what this is kind of showing right here, when we go and implement the MiniMax algorithm, we'll see that it can look, 8, 10, 15 moves ahead if we implement it efficiently. So in theory, the AI should be able to have an advantage over human players, which is what makes this so cool. So in order to choose the best move to make from here, we have to kind of decide or assign decider or deciding algorithms to each one of these nodes. So in order to decide what let me go back. In order to decide what the best move to make here is, we have to decide what the best move to make here is. We have to decide what the best move to make here is, all the way down to the bottom of the graph. And the best move to make is going to depend on what player is playing. And we can kind of think of this as a spectrum, right? It's just a one-dimensional line where good moves for one player are on one side of the spectrum, good moves for the other player on the other side of the spectrum, and kind of like neutral moves are somewhere in the middle. And their value or in there accordingly. And so just the canonical terminology is we've got this maximizing player and the minimizing player, and we use the spectrum as just the number line. So a maximizing player is trying to get or make moves that result in game boards that have a high value, while minimizing players are trying to get or trying to find game boards that have low values. And we'll talk about what values mean here in a second. But the intuition should be pretty clear in that we start with one player and we alternate to the other, and if we had a bigger graph, it would continue alternating all the way down to these kind of gray nodes. And what these gray nodes are, they're kind of terminal states. Either the game has ended because one player has won and there's no need to look any further, or we've kind of set an arbitrary cutoff. So if it's a really big game tree, we don't really want the AI to be processing for years and years to get all the way to the bottom. We can set some sort of reasonable cutoff and say we only want it to look 10 moves ahead, and so it'll only look that far. You can see in this game tree, I've set it to only look 2 moves ahead. And that's just for purpose of illustration. Hopefully, when we get to the Mancala game, we'll be able to set it to look far further ahead. So, the other key concept about MiniMax is that the only nodes that have inherent scores are terminal nodes, so terminal game states. So either the games that have been won or lost, or nodes that are at that maximum search depth. Like I said, if we don't have enough time, we then look no further, and then what we do is we assign a value to a game state with a heuristic function. So let's look at this trio of game states here. these game states terminated because we reached the maximum depth of 2. And when we ran our heuristic function, we saw that this game state was slightly better for the maximizing player. This game state was a little bit less good for the maximizing player, but still in the maximizing player's favor. And then this game state was very good for the minimizing player. And so that's what it means for game states to have scores, right? So all it means is that this game state, whatever configuration of the game that we're in right now, is very, very good for the minimizing player. Conversely, we can look kind of here, and this is I'm going to say that these are the trio of nodes that represent terminal nodes. So the game has either been won or lost at these positions. So if the game is won by the maximizing player, we want to assign it like the highest possible positive score. So infinity. If it's won by the minimizing player, we want to assign it the lowest possible score, negative infinity. And if it's a tie, so some games can result in ties, think tic-tac-toe, for example, we'll assign it a 0. So it's not really good for either player. Now, the rest of the nodes receive their scores from the bottom up. So this node would look at all of its children, and then it would, since it's the minimizing player, this red node, it would find the minimum of all of the children. So in this case, this node, if it was a rational player, is going to obviously pick the node that results in the best game state for its strategy. And we do that for all of the nodes, and we work from the bottom up. So we can resolve this one, we can then resolve this one, we can then resolve this one, but not until we have all 3 of these things resolved can we resolve this, this initial node here. And you'll see that at the very top, this maximizing player is going to want to move in this direction because it's the maximum score that it can receive, or that it has available to it. And so even though it's a negative number, so not going to be good for the maximizing player, this negative 40 is better than the negative 50 and certainly better than the negative infinity. So some other considerations are that we don't want to just kind of do this score assignment as well. We also need to have some way of tracking what moves resulted in each score so that we can replicate this play. So for example, if we just passed up the scores in this, and I would know that this maximum node has a negative 40 value, but I wouldn't, if I didn't keep track of it, I wouldn't know which direction the negative 40 came from. Additionally, and this is actually the really key concept. So MiniMax itself, it should be pretty intuitive. I mean, you've played games kind of in this style all of your life. But the important part, besides getting the algorithm correct, is coming up with a good heuristic function. And this is really going to drive the goodness, I suppose, of your AI strategy. It doesn't matter how far. Well, I guess unless you can look and traverse the entire game tree, which is an unreasonable assumption in most games. It doesn't really matter how far you can look ahead if your heuristic function isn't returning things that are sensible. And the better your heuristic function, the less distance you have to look ahead to get to pick a quote unquote good node or a good move. And so optimizing this heuristic function is critically important. Another kind of more subtle thing is that this heuristic function is going to be called a lot. If you have a game tree like this, these leaf nodes, is what I'll call them down here, are going to be the most populous type of node in your tree. They're going to make up just about half of the nodes in the tree. And so if your heuristic function is slow, let's say it's like an n squared or n cubed sort of algorithm, your search is going to be very, very slow. So creating not only like a good heuristic function, but a fast heuristic function is kind of the magic sauce. So before we jump into talking about alpha beta, let's just get MiniMax implemented and working. So I'm not going to go over all of the rules for Mancala. We are going to implement it. Or actually, we've already implemented kind of the whole game data structure, so you don't really need to worry about that. We're just going to be worried about implementing the MiniMax algorithm. But it'll make a lot more sense if you have a good understanding of it. So we've included a link here with some very detailed instructions about how to play, but we have one adjustment from the official rules. So normally, if you are depositing the last stone in your turn into your store, you will receive an extra turn, so you get to play again. But we are not going to be doing that in our game. Why? Because that would break the alternation between min and max. If you give two turns to the same player in a row, we obviously don't alternate between the min and max player. And so just for the this example, we're going to take that out. But as a challenge, once we're done with this, you might think about how you might implement that functionality in your code after we get done with kind of the basic min-max algorithm. So let's take a look at the code base that we've distributed to you on GitHub. So we've got this board class here that represents the Python representation of like a Mancala game state. So we've got our constructor. The make move is kind of the big function here. You can read through the logic; it's all pretty well documented. But essentially, we can pick one of the buckets, and then we execute kind of the Mancala algorithm of dropping stones and all of the subsequent buckets in the proper manner. And so again, read up on Mancala if you haven't already. This should be clear after you read the rules. Then we have the children. So this should look pretty familiar if you've been watching the previous videos. Children just is a list of tuples of the successor game states. So you've got the move the move to make the child, and then you've got this new game state object. And there's a list of all of the valid children of it. So if we come back to our PowerPoint real quick, let's see here. It would just generate, so if we called child or children on this, it would generate all of these nodes. And if we called children on this, it would generate all of these nodes. So that's sort of what that does for you. Is over is a check to see if the game is finished or not. Score returns the final score, so the number of stones in player one's bucket minus the number of stones in player two's bucket. So if it's a positive score, that means player one wins by X points, and if it's a negative score, then it means if it's a positive score, player one wins by X points, and if it's a negative score, player two wins by X points. And then we have just a nice little visual representation. You can see down here, I was testing a little bit earlier. So this is what the Mancala game will look like. Here are all the buckets. I believe that they're numbered starting at 0 all the way around counterclockwise. And these are the number of stones in each bucket. These little end pieces are the stores. So here's player one's store, here's player two's store. So if you're all confused, I would recommend that you just pause the video, take a moment and just internalize what's in here, because the rest of this will make a lot more sense if you know what's going on. It's not too complicated, but I know I'm breezing over it pretty fast as not to waste everybody's time talking about this in the video. The other thing we have here is the driver function. So all this is doing is it's simulating a game, and this should look pretty clear. We've got some timers here that we're going to use to show how the alpha beta improvement works, and then we just have this while loop. So while the game's not over, make or find a move. Either player one or player two is going to find a move, and then make that move, and then flip the turn. So until the game is over, and then print out the final score. So that should be pretty clear. And what we need to do in our our task is to implement this find move function and this heuristic function. So the heuristic function is just taking a game board and evaluating the goodness. So, player 1 is going to be the maximizing player, the player 2 is going to be the minimizing player, and then this find move is going to be in charge of implementing that MiniMax algorithm. So let's take a look first at the heuristic function. So we want to return high values for player 1 and low values for player 2. So I'm going to propose that we just do a kind of count of the stones on each player's side, because the more stones you have on your side, kind of the better shape you are. And then we'll do something like player 1 stones minus player 2 stones, and that'll hopefully represent the at least some measure of goodness. So we'll say player 1 stones equals 0, and then we're going to say for I in range board.buckets. So these every I is going to be on player 1's side. And then we're going to say player 1 plus equals board.board I. So this is counting, player 1 stones. Oops, I got a couple typos. So this is taking all the stones in the buckets and adding it to player 1 stones. And then, so we've got the stones that are on the player's side, but we also have the stones that are in player 1's store. And I'm going to say that the stones that are in player 1's store are going to be worth, let's say, 50% more than stones that are just on its side, because those have already been captured and those can never be lost. So that might be a good representation. So we'll say player 1 plus equals board.board board.buckets. This is how we get to player 1's store, and so that'll return the number of stones there, and we'll do times 1.5. So those are going to be worth a little bit more. I don't know why I keep doing that. Player 1 stones. Okay, and then we're going to do something very similar for player 2. So player 2 stones equals 0. So their range is going to be a little bit different. So it's going to be for I in range. It's going to start right after the player 1's buckets. And it's going to go all the way to the end here. And we're going to do the same thing. So player 2 stones plus equal board.board I. Just as a quick clarification, I'm sure you picked this up if you had been looking at the code, but this board.board would be more semantically clear if it was named board.buckets. So these are just a list of all of the different buckets on the board. And then we were doing player 2 stones, and we're going to do the same thing of adding their store, board.board buckets. So their stones in their bucket is going to be worth 50% more than the stones just on their side. So we're going to say times 1.5. Okay, so now we've got the kind of score for player 1 and player 2, and what we're going to do is we're going to return player 1 stones minus player 2 stones. And so this will be like an okay heuristic. We could tinker with it a little bit more to maybe optimize it, but we can see it's probably going to be fast. It looks like a linear time algorithm, as well as, it seems fairly reasonable. One of the things that you could do later is go and see how changing this heuristic function, maybe by changing this parameter here, so how much additional value we're giving to stones in a player store. How changing that affects the moves that are chosen by our find move function. But I'll leave that as an exercise for you guys. Okay, so now this is the big doozy. We have to now implement the MiniMax algorithm here. So what we're going to want to do is we're going to want to have something that is recursive, keeps track of a depth and whose turn it is, as well as the current board. So we want to keep track of kind of three things in a recursive function. Since this thing doesn't take all of those arguments, I'm going to create like a little internal function that does, and we'll call this internal function from this outer function, and it'll hopefully it'll recur. So I'm just going to call this find move helper. I'm going to say current board depth and is max. So this will be the three sort of things that we want. So how we would call this from the outside is, well, let's first say what's this going to return. So the find move helper, if we remember, we go back to our PowerPoint here. It needs to do a couple of things. It needs to return the scores up here so that the find move helper, so this find move helper needs to return 5 so that this find move helper that's called on this node can put 5 into their minimizing equation. And then this node here needs to return -50 so that this node's find move helper can put -50 into this into their maximizing equation. But, like I said earlier, this other consideration, we need to keep track of the move that resulted as well. So we're going to have kind of two different things that this is going to return. So it returns a tuple. Let's call it the score. So I'll call it best score, and then also move for best score. All the moves are just integers, so representing the bucket that we selected as we go in the Mancala game. So after we define that function, we'll get to in a second, we can break apart the things like this and call find move helper on the board that we're passing in here, right? As well as a depth limit. So you can see in the constructor for player, we are going to set a depth limit. So this player is going to be able to look that far ahead. So we're going to say, so we'll just pass in the depth limit here. And then the final thing is, so our thing is it a maximizing player? So just arbitrarily, we're going to say that the maximizing player is going to be player 1. We've defined that in our heuristic below here. So high values for player 1. So our maximizing player should be player 1. So we have this is player 1 Boolean right there. And so if it's is max, it should be self dot is player 1. And that'll hopefully map there. And then what we want to do is, so this find move, it's not really finding the optimal column. Find the optimal bucket to select stones from. And what we want to do here is we want to return just that move component, right? So at the end of the day, we don't really care about the score. We just want to know, like, what should we do at this point? The score is used as kind of an internal mechanism for this helper right here. Okay. So the first thing that we want to do is check to make sure that this current board isn't either a terminal node or at our maximum depth. And so we'll handle those separately. So if current board dot is over, I believe is the function, then we want to return a let's see here, board. So we could return the score here, but I said in the PowerPoint that it'd be better to return infinity or negative infinity. So let's stick with that. So if it's if it becomes the maximizing player's turn right here, and the board is over, that means the minimizing player is the one that made the move to cause the game to end. And so what we're going to do is we're going to do negative math.inf if is max, else we're going to return math.inf. So that'll be the score. Our move is just going to be -1. We don't really need to keep track of any move here because we didn't make a move, right? The game was over. And so -1, if we ever have a negative number as our move, we'll know that we have an error somewhere because that we shouldn't have been making a move. So let's see here. The other way that we might terminate is if we're at our depth limit. So every time we recur, I'm going to decrement the depth by 1. So I'm going to say else if the depth equals 0, meaning we have decremented the depth all the way down, we're going to now do our heuristic function here. So this is where we do that self.heuristic. We pass in our board. And again, we want to return -1 because we didn't make a move. We're just returning a value. The only time that we make a move is when we actually do the recursion. So -1 makes sense in that sense. So if it's not sort of this bottom of the tree sort of or node, then we should continue to look further. So we can go ahead and get the children. So we'll do children equals current board dot children. Okay, so both the minimizing and maximizing cases look pretty similar. And we'll talk about that here in a second. But I'm just going to create kind of the generic template for what we should do. So originally, let's set our final move equal to -1. If we ever return a final move that is -1, that means that we've got an error. So that's a good initialization value. And then we're going to say for every child in children. And remember, children is a list of tuples that actually contain the child move as well as the child board equals child. And we are going to say we're going to get the value from doing one of the recursions. So I'm just going to say temp value equals find move helper. We are going to recur on the child board. As well as we're going to, like I said earlier, we're going to subtract 1 from our depth, and we're going to keep subtracting 1 at every recursion until we get to this depth equals 0. And then we are going to flip this Boolean. So if it's maximizing right now, it's going to be minimizing next. If it's minimizing right now, it'll be maximizing next. And this is going to return both a move and or it's going to return a score and a move. And really, we just want to get the score here because that's going to be our temp val. Now, if let's say I'm gonna make this function, this little pseudocode function. We haven't implemented it yet, but I'm just gonna say if we should replace our current value with our temp value, then we're going to do a couple of things, and we haven't done all this yet. Final score equals temp val, and final move equals child move. So this should replace function is really going to be the only thing that changes between the minimizing and maximizing player. And so I'm going to come up here, and I'm going to actually create another inner function that is parameterized by whether we're the maximizing player or not. So if it's isMax, we'll do one thing. Otherwise, we'll do another thing. So if we are the maximizing player, we want our initial score to start as low as possible. So we'll initialize final score to be -infinity, so that unless so that any score that we receive from our recursion is going to be greater than it, and we can immediately replace. So final score equals negative math.inf. And then we'll do should So this is where we're going to define our should replace. So we're only going to replace this final score if we have some sort of lambda x here, if x is greater than the final score, right? We don't want to replace this final score unless we get a temp value that is greater than the current final score. So if it is greater, then replace the final score with that temp value, and then replace the final move with the child move. So whatever move we did to get that temporary value, we want to save that because we're going to return it here in a second. So otherwise, it's kind of the opposite, right? So for the minimizing player, we should have the highest possible score at the beginning so that we immediately replace it upon our first recursion, or our first kind of iteration through this loop. And then should replace is going to be equal to lambda x. X is less than the final score. Okay, so we've got all of this pretty much set up now. I mean, it really is just as easy as that. And we need to make our return call at this point. And if we look back at our kind of definition here, this needs to return the best score and the move for the best score. And so we have those saved in final score, final move. And it might even be better, just for semantics sake, since we defined this stuff up here, to do a little refactoring and just have this be something like best score, and then instead of final move, we can do something like move for best score. So if that makes things clear, I'm glad. Otherwise, I guess this is probably just better for people who are reading it later. Okay, so we ended up making a small error in that previously we were returning when the board is over dependent on whose turn it was. And in some games, like tic-tac-toe, for example, that'll work perfectly fine. However, in Mancala, it doesn't really matter whose turn it is with regard to who is winning when the game finishes. What's actually more important is what the score is when the game is over. And so what we can do here is we can just take out the thing that we had before, and we can return the board.score. So this will return a positive number if player 1 wins, or a negative number if player 2 wins. And so it should work, and everything should go fine. I know this breaks our convention of positive infinity or negative infinity, but it really shouldn't impact anything in the long run. So we'll try it again with, or we'll run our driver function with that small fix, and we will hopefully avoid having some sort of infinite loop, which is what we had, what we would have had previously, or I guess really more just like nonsensical results. So we'll let it run. I think this is going to take about 30 seconds or so to get all the way through. I'll show you guys how to optimize this here in a second, but let's make sure that we've faithfully implemented the MiniMax algorithm. Okay, so you can see here we got all the way through. It ended up being player 2 winning this game because they ended up having 16 more stones in their bucket than the opposing player, because all of these stones right here would have been moved into player 2's bucket, or player 2's store, once the game was over. But what's kind of more important or more interesting in my opinion is the fact that it took so long to solve this or to play this game, even though we were only looking, I believe, only 8 moves ahead. So not super great. Now, what we can do is we can take a look at the alpha beta pruning and get a sense for how we can optimize this and hopefully resolve or get the same exact answer, but in a lot less time. So we'll transition over to looking at that PowerPoint right now. Okay, so let's talk a little bit about the alpha-beta pruning optimization. The objective behind this is that we want to eliminate the traversal steps of the graph that don't add any information. So in other words, we don't want to expand nodes that cannot possibly impact the decisions of a rational player 1 or player 2. And the way we can do this is actually pretty elegant. Simply by adding 2 additional pieces of information to the evaluation of every node, we can determine whether that node is going to add new information or whether it's not. So the 2 pieces of information that we're going to add are alpha and beta, and those are going to be added as a part, so in referencing to our Python code, those are going to be added in that recursive function. Alpha represents the best possible score that the maximizing player is assured of. And so what does that mean? It means that if we're at some arbitrary point in the processing of this game tree, then we have probably processed some nodes before this point. And based off of those nodes, we kind of have a worst case scenario for the maximizing player. They've already have a score that they could receive if all of the previous processing or if all of the subsequent processing returns scores that are lower than what they've already looked at. And so it's kind of the best possible score that they're definitely going to get, meaning that they have seen this score and it's the best score of what they've already seen. And that's kind of vice versa for beta. So it's the best possible score for the minimizing player, meaning it's like the lowest score that they've seen, that we've seen so far in the processing of the game tree. And then if we ever come to a node where the alpha that we pass in is bigger than the beta, then we can stop expanding that current node. And it might seem a little bit confusing at first. I'm going to walk through kind of the intuition, and then we're going to go through an example. So why would we need to, or why does that current node not add any information, and why can we ignore it? Well, alpha and beta are passed down from parent nodes. So it means that alpha and beta are passed as arguments to that recursive function. And they represent the scores of those previously processed decision paths. So they might be sibling nodes, they might be uncle nodes, it could be whatever. It's stuff that we previously processed. And based on what we've previously processed, we have a best possible score for the maximizing player and a best possible score for the minimizing player, alpha and beta respectively. So let's look at it from the perspective of if the current node that we're processing is a maximizing player. If we're processing that maximizing player and alpha is ever greater than beta, then we can stop processing. Why? Because the minimizing player is guaranteed to be, or the parent is guaranteed to be a node for the minimizing player, right? Because we alternate between maximizing and minimizing. So the maximizing player that we're currently at, so the current node, is always going to return a value that's greater than or equal to alpha. And if we return a value that's greater than or equal to alpha, if you think back to our MiniMax our MiniMax algorithm, then the minimizing player will never pick this node or move because alpha is greater than or equal to beta. So the value that we're going to return is going to be greater than or equal to alpha, guaranteed. And alpha is always going to be, and we've already determined that alpha is bigger than beta. And beta, if we're a minimizing player, is only going to be replaced if the value that is returned from this current node is less than the current beta. So in other words, the minimizing player will never pick this node because it's already found a better decision path representing by beta. And so like this node, any further expansion of this node is just going to be redundant. All further expansion could do is increase this value, but increasing the value isn't going to ever impact the decision of our parent. And that same is true for the for minimizing player. So if our current node was a minimizing player, everything would just be opposite. So I understand 100% that can be a little bit confusing. So let's take a look through a graph or a graphical example. So we start out with this game tree, and an important thing to note is that we always start out with alpha equal to negative infinity and beta equal to infinity. Why? Because since we haven't processed any nodes so far, the best score that the maximizing player is guaranteed so far is the worst possible score that it could get. Right? It's not assured of really anything, and vice versa with the minimizing player. So we put in the worst scores that the alpha or that the minimizing player and maximizing player can receive. So we pass this in as the initial arguments, and then we process down to the left. And then what we're going to get is, once we process this child, right, we get a 5, we can replace beta with that 5. Why? Because 5 is definitely less than infinity. So our new kind of best decision path is going to be the decision path that comes down here to this 5, at least according to this node's objective function. We can see the same sort of process with the 3, right? 3 is less than 5, so beta gets replaced. Negative 50 is less than 3, so the 3 gets replaced. And then what we're going to do is we're going to return that negative 50 up here. And so actually, so this is where it gets a little confusing. The alpha of this node is now going to be negative 50. Why? Because this node is, or given the choice between these 3 options, is always going to choose this option, return negative 50. And so since the maximizing player doesn't control the decision of this minimizing player, it essentially says, of all the nodes we processed, this, I guess really it's looking locally at just these children, right? And it's saying, okay, this child is guaranteed to return a negative 50, and since I haven't looked at these 2 yet, the best thing that I'm assured of is this negative 50. Okay, so we're going to go ahead and pass that down to our second child. And we have those initial arguments, and then we process this negative 60, and we can see our beta gets overwritten by this gets overwritten by the negative 60. Why? Because negative 60 is less than infinity. So given this node's worst case move, or I guess the best possible move it's assured of, is the path that goes to here. But notice that now we have an alpha that's bigger than our beta. So whatever this node returns is guaranteed to be less than or equal to this beta, right? I mean, we could just look at it. Processing down to the 5 is not going to replace the beta. Processing down to the 4 isn't going to replace the beta. It's always going to return this negative 60. But since our parent already has the option to choose a negative 50, it's never going to choose this node. So essentially this node has just become completely irrelevant, and we can immediately stop processing. So we can just not even bother going down to those nodes anymore. We can return early and pop back up. We don't replace anything here. And instead we go and look at the next child. So the next child, we start out with those values. We see this negative 75, and then we replace our beta with negative 75 because negative 75 is less than infinity. Again, we have this alpha is greater than our beta, and for the same reasons, we're going to be guaranteed to return from this node a value that's greater or that's less than or equal to this negative 75, which means that this node, our parent node, is never going to choose it. So this node just became irrelevant, and we can stop processing it immediately and get rid of, oh, I don't know why I did that, and get rid of all of the, and not even worry about processing any of the children any further. And so this doesn't look like maybe that big of a speed up right now, but when you consider that if we're doing a depth of 8 or 10 or 15, each one of these nodes might represent a massive subtree, and so we're able to cut down the processing time pretty significantly. I think that the average speed up is something like I don't even want to speculate. You'll have to look that up on your own. And we can test it empirically here on or when we implement it in our Python program. And that's exactly what we're going to do. And we'll take a look at that here in a sec.